Hi guys! So we're moving on to discrete probability distributions. We learned probability in the previous chapter, and now we're going to start building our distribution using probabilities. Okay, we're going to start by learning what a random variable is. And essentially, we're going to be able to take a qualitative variable and turn that into a quantitative variable. Okay, let's start by an experiment. All right, so we're going to use flipping a coin as our little experiment. Okay, so what kind of things can we get from flipping a coin twice? Right? So let's define our sample space here, right? So we can get two heads, we can get two tails, we can get heads and tails, or we can get tails and heads, right? So we have four outcomes in our sample space. Now, how I have this written, these are qualitative variables, not quantitative variables. And with qualitative variables, we really cannot do much as far as calculation goes because these are letters, right? And we really cannot do addition, subtraction, multiplication, division with words. So what we could do is this. Let's say we're interested in counting how many tails we get by flipping a coin twice. So we could define a capital X to be a number of tails, right? So we could count the number of tails rather than listing it out as an outcome. So if we go through our outcomes here, this one has 0 tails, and this one has 2 tails, right? And this one has 1 tail, this one has 1 tail, right? So our options, our sample space for this, capital X, will be X equals 0, 1, and 2. No tails, 1 tails, and 2 tails. Okay, so when we do this, now we've turned this qualitative variable, right, into a quantitative variable. And this X right here, okay, this X, this one right here, okay, is actually called a random variable. So if the outcome of a probability experiment is a numerical result, then we say that outcome is a random variable. All right, so let's read the definition. Random variable is a numerical measure, important numerical measure of the outcome from a probability experiment. So its value is determined by chance. Random variables are denoted using letters such as capital X. So in our coin flipping example, the random variable X is the number of tails in 2 flips of a coin, and the possible values of the random variable X are 0, 1, and 2. Now, our particular example of flipping a coin and counting the tails was a discrete random variable because it had a countable or finite number of values. Another way of looking at this is that we can plot the values of a discrete random variable on a number line, and there will be space between each point. So X equals 0, that means 0 tails, right? 1 tails, 2 tails, 3 tails, 4 tails, like that. A continuous random variable, on the other hand, has infinitely many values. So when we plot those on a line, right, it's just a continuous line like this. So there's no spaces in between the values, right? Since a value of a continuous random variable can take on any number between an interval. All right, so let's look at some examples. Example 1. Determine whether the following random variables are discrete or continuous. State possible values for the random variable. Question A. The number of A's earned in Mrs. Forbes' statistics class with 50 students enrolled. Okay, so the random variable here is the number of A's earned in my class. So X is the number of A's, right? Okay, because we can count those, right? It is a discrete random variable. I'm going to put RV for random variable. So what are the possible outcomes for this one? Well, it is possible that no one gets an A in my class. Oh, that will be really sad, okay? But yeah, that could happen. And it is possible that one person gets an A, or it is possible that two people get an A, or three students get an A, and so on, right? And it could go all the way up to 50. Why 50? Because we have a total of 50 students enrolled, right? So all 50 students could get an A, right? Okay, so X will be will go from 0 to 50. All right, those are the possible outcomes of the random variable. Okay, question B. The speed of the next car that passes a state trooper. Okay, so the random variable for this one be the speed. Okay, and it is a continuous random variable. Why? Because speed is measured, right? Now, the possible values are, well, you can say X is greater than 0. You can say the possible values are all positive real numbers, right? Now, since we don't know the exact upper bound for this, we can just leave this as an open-ended interval. I mean, we know that something like 500 miles per hour does not really make sense for this, but just leave it as open-ended interval is fine. Okay, question C. And I would like you guys to try this one on your own. So go ahead and pause the video and try it. And when you're done, come back and check your answer. Okay, go ahead and check your answer. So this is a discrete random variable, and the possible values are 0, 1, 2, 3, and it could go all the way up to whatever number. So you can just make it an open-ended, just like before. Okay, but this one is discrete random variable, so you have to list numbers like 0, 1, 2, like that. All right? Okay, so the important thing to remember is that the actual value of X is determined by chance, right? So for example, we don't know the probability of two cars that come to the drive-through. It's up to people. It's determined by chance. So all of these different values right here, okay, have different probabilities. So we organize the information using table, graph, or formula. Now, probability distribution provides the possible values of the random variable X and their corresponding probabilities. A probability distribution can be in the form of a table, graph, or mathematical formula. Okay, so it follows two rules. So you're gonna have to check two things. First, you want to make sure that each probability must be between 0 and 1. So each probability must be between 0 and 1. Okay? And the second rule, if you add up all the probabilities, you should get 1. Okay, so parts add up to the whole, right? All right. Now, notice that we have a probability distribution, which is a distribution, right? So whenever we have a distribution, we look at three things. What are they? Well, the shape. That's the first one. Shape of the distribution. And we look at the central tendency. Such as mean and median. Mode, not so much. Okay, we focus on mean and median. all right? And the spread, okay, of the data, which is the standard deviation or the IQR. Okay, let's look at an example of a probability distribution in the form of a table. All right, the table below shows the probability distribution for the random variable x, where x represents the number of movies streamed on Netflix each month. So it looks like the value of a random variable ranges from 0 movie to 5 movies a month. Well, obviously, this is a little outdated data, and I think people sometimes stream 5 movies a week or more these days, right? But this is what it is. Okay. All right. So it's a probability distribution. So let's ask ourselves these questions. Is each probability between 0 and 1? Oh, well, we can just do a quick scan here, right? First one, 0.06. This will be the probability that someone will stream 0 movies a month, right? So 6% probability that the person streams 0 movies, right? Okay. And next one is 0.58, 58%, 0.22, sorry. 0.10, 0.03, 0.01. Good. They're all between 0 and 1. Perfect. No negative numbers. No numbers more than 1. Perfect. All right. Second rule. Do all the probabilities add up to 1? Well, we can check over the first one, first of all. Okay, so this one was okay, right? Okay, the second one. Go ahead and add these numbers up, guys. Do they add up to 1? 0.06. plus 0.58 plus 0.22, and then you're going to add all the way up to 0.01. This should add up to 1. Go ahead and check. Yep. All right. So what we can do with this is something really similar to what we did in the frequency distribution chapter. So once we had our frequency distribution, we made a frequency histogram, right? So now that we have our probability distribution, we can make a probability histogram, okay? And it is created the same way. The horizontal axis corresponds to the value of the random variable. So in our case, number of movies streamed, okay? And the vertical axis corresponds to not frequency, but the probability that each value of the random variable will occur. Okay, so let's draw a probability histogram for this. All right, so the horizontal axis, again, number of movies streamed. It goes from 0 to 5. Okay, that's these, right? Okay, and the probability, when you look at the table here, the highest probability is 0.58. Okay, so how many do we have here? 1, 2, 3, 4, 5, 6. Okay. So how about we make each tick mark 0.1. So 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. There we go. That will work, right? Okay, we're ready. So for discrete variables, the number is normally right in the middle of the bar, and the probability that they stream 0 movies, right, is 0.06. So it's a little over halfway on the first notch, so it's going to be somewhere here. Okay, right? So this is for x equals 0. Okay, it's 0.06. 0.06. Okay, all right. And how about when x equals 1? That's 0.58. Okay, so that's almost all the way to the tippy top. Okay, so this is 0.58. Okay. All right, so how about 2? The probability is 0.22, so it's gonna be somewhere here. Like that. Okay, and 3 is 0.10. Okay, and 4, 0.03. Okay. All right. And 0.0145. Okay, it's really skinny. Okay. All right, there we go. Okay, so now we have our distribution, so we can talk about the shape, right? What shape is this? Yes, you guessed it. Skewed right, right? Skewed right distribution. Okay, so what I want to do now is I want to focus on this rectangle right here. This one. Okay, this rectangle. Okay. All right, so I'm going to bring this one down. And we're going to talk about the area of this rectangle. Now, what is the width of this rectangle here? Well, these discrete variables up here, they're kind of like a midpoint. Okay, kind of like a midpoint here. Okay, so we're going 0 to 1, 1 to 2, 2 to 3, and so on, right? So the width is 1. And what is the height here? The height is 0.22. So the area of this rectangle is 1 times 0.22, which is 0.22. Okay, which is the same as the probability of the value of the random variable right here, right? Because the width was 1, so the area is the same as the probability, which is the height of this rectangle. So let's write that down. It's actually very important. Area is the probability the random variable has that value. Okay, area is the probability itself. Okay. Okay, let's continue on with the mean of the probability distribution. Okay, it's the same concept as a weighted mean. So here's the formula. We're gonna use mu of capital X, or you can just say mu of X equals the sum of the value of a random variable X times its corresponding probability. Okay, so let's do an example by hand. Okay, so we're gonna go back to the Netflix example. Compute the mean of the probability distribution. Okay, so first you're gonna be multiplying each value of the random variable by the corresponding probability. So 0 times 0.06, that will be just 0. And 1 times 0.58, that will be 0.58. 2 times 0.22, that's 0.44. 3 times 0.10, 0.3. 4 times 0.03, 0.12. And the last one, 5 times 0.01, so that'll be 0.05. Okay, so once you get these products, then you're gonna add them all up. Okay, so when you add them all up, you should get 1.49. And what is the units? Streamed movies. Right, so this is it. This is the mean of the probability distribution. And we're going to talk about the interpretation in just a second, but I want you to focus on the calculation for now. Okay, now let's use our calculator to find the mean. Okay, so take out your calculator. All right, so first you're gonna type in your data in L1 and L2. Okay, so I already did that. So under L1, you type the values of x. Okay, and then under L2, you type the values of the probabilities, right? Okay, and once you did that, you're gonna go to stat, and you're gonna go to calc. Okay, and we want number one bar stats. So go ahead and press enter on that. Okay, and then you're gonna type second, you're gonna press second L1, and then press comma, and you press second and then 2. So you're listing 2 lists right here, L1 comma L2. Okay, and then you press enter. There you go. So 1.49, that is the mean of the probability distribution. Okay? Okay, so there is only 6 possible values here. Okay, so this was fairly easy to calculate by hand, but if it's larger, then that will be a kind of tedious to calculate by hand. So you're more than welcome to use your calculator on this, okay? All right, so let's see how we can interpret this mean. So I want you guys to recall how we interpreted probability in the previous chapter. Well, we used the law of large numbers, right? So we do the same thing here because mu of x, the mean, right? Oh, I did not actually write the symbol here. This is supposed to be mu of x right here, right? That's the mean. Okay, so the mu of x is from a probability distribution. So whenever we have something related to probability, we interpret it using the law of large numbers. So suppose that we repeat a probability experiment many times. Well, let's say 100 times with outcomes x1, x2, x3, all the way up to x100, right? So let's write that down. Suppose a probability experiment is repeated many times, say 100 times with outcomes x1, x2, x3, all the way up to x100, right? So x1 is the number of movies streamed by customer 1, and x2 is number of movies streamed by customer 2, and so on. So you repeat it 100 times. Now, if we calculate x bar, right, from that sample, meaning the average, right, you find the average number of movies streamed by 100 customers, what do? We add up all the data values and divide the total by 100, right? So we get, right, so here, if we find x bar, which is x1 plus x2 plus all the way up to x100, and we divide that total by 100, right? That will give us x bar. Then what we expect is that we expect that the value of x bar will be pretty close, right? Pretty close to the value of mu of x, which is the mean of the probability distribution up here. Okay, so let me explain a bit more about this, right? So this chunk of data right here, okay, it represents the number of movies streamed on Netflix by 100 randomly selected customers in a single month. So the first one we surveyed, the person streamed 1 movie per month, second person, 2 movies, third person, 1 movie, and so on, right? Now we're going to compute the mean of the movies streamed from this list of 100. So what that means is that we're going to add up all these 100 values and divide the total by 100 people, right? Now if you do that, I already did it here, okay? If you do that, you're more than welcome to check it on your own. We would actually get 1.49. Okay, now, so again, when you go back to the definition here, right? If we repeat the same experiment, meaning if you ask many customers how many movies they stream per month, right? So if we survey, let's say 100 customers, then the X bar, the average number of movies that they watch per month, will approach the value of mu of x, which is the mean of the probability distribution. So here's a nice little visual here, right? The horizontal axis right here is the amount of trials, right? So it's like this 100 means like you're sampling 100 people. Okay, 50 is like sampling 50 people. And the vertical axis is the value of the corresponding mean. And like you can see the word mean. Okay, that's going to be X bar. All right. So when number of trials is pretty small, like let's say 0 to 10, somewhere between 0 to 10, somewhere here, right? The mean fluctuates. You see this? It's really unstable. But as we sample more people, let's say 100, right? The mean becomes more stable and it approaches, this horizontal line, by the way, is mu of x. That's the value of mu of x, which is 1.49. So the mean value, x bar, will approach mu of x, which is the mean of the probability distribution. Okay, so this part right here summarizes what we just talked about. As the number of trials increases, X bar, which is the mean of the sample, approaches the value 1.49, which is the mean of the probability distribution. That is, as the number of trials increases, the mean number of movies streamed on Netflix in a single month approaches 1.49. All right, so mu of x, because it happens when we have a lot of probability experiments, a lot of trials, right? So we can also think of it as what happens in the long run. So sometimes it's also called the expected value. Expected value. So mu of x is the value that we would expect to get in the long run. And we will use E of x for the expected value, this notation, E of x. Okay, so let's look at an example using the expected value. All right, example. A term insurance policy will pay a beneficiary a certain sum of money upon the death of the policyholder. These policies have premiums that must be paid annually. Suppose a life insurance company sells $250,000 one-year term life insurance policy to a 49-year-old female for $530. I always like to highlight things that I think are going to be important. All right, according to the National Vital Statistics Report, the probability that the female will survive that year is 0.99791. Okay, compute the expected value. Here we go. Expected value of this policy to the insurance company. So this part to the insurance company is actually important. So we want to know how much money the insurance company is going to make, right? So expected value is your key word right here. So the expected value is the same as mu of x. So mu of x is the mean of the probability distribution. And a probability distribution has a random variable and the corresponding probability. So we can start here. So we want to know the expected value of this policy. Well, it depends on what happens to the customer, right? So let's look at the qualitative variables first. Okay, so I'm going to make a little table here. All right, so there are two possibilities, right? Two possible outcomes. The first one will be the client survives. Okay, and the other outcome will be the client dies, right? And we're going to let X, our random variable, be the payout. Payout will be that money gained or lost. It depends, right? So if the client lives, right, if she survives, then we know that she will give $530 to the life insurance policy. So the life insurance company will make $530. Okay, they'll make $530 from that person. Now the probability of that client living is 0.99791. So it's given. So probability will be 0.99791. Okay, now let's look at the flip side. If the woman dies, well, first, the insurance company will still get $530 from the client, by the way, for the year. But they have to pay, so it's going to be a negative number, right? They're going to have to pay how much? $250,000, correct? Okay, and it actually ends up being, let me write this one out. So negative, because we're going to do 530 minus $250,000. So they make 530 still from the woman, but they're going to pay $250,000. So you subtract that money. So that's going to be negative $249,470. Okay, so this is how much they're losing, right? Okay, if the woman dies. Okay, because they have to pay out the money. All right, now the probability of that happening will be what? That will be the opposite, the complement of the survival rate. So you go 1 minus 0.99791. So the probability that this person dies will be 0.00209. Pretty small, right? So notice when we're doing this complement thing here, it's becoming a probability distribution because now when we add these probabilities up, we know that they add up to 1, right? Okay, so we created a probability distribution right here. Nice. Okay. Now we have that, we can compute the expected value, which is just the mean of this table, right? So if you want to use your calculator, then you can just put this right here, x values into L1, and you put the probabilities into L2, and you find the mean. Or if you want to do this by hand, then we can multiply each x value by the corresponding probability, right? So 530 times 0.99791, you're going to get something like 528.8923. Here, what we're doing is x times probability of x, okay? All right. And then down here, you're multiplying negative 249,470 times 0.00209. So you get negative 521.3923. Okay, we don't like rounding decimals until the very end. Okay, so after you get these two numbers, you can add them up, right? You can add these two numbers up, which will give us 7.5. So that's $7.5. Okay, so that is our expected value. This is our expected value, E of X, which is the same as mu of X. So we just found the expected value from the insurance company's perspective is $7.5, right? So what does $7.5 really mean in this case? Well, again, if we repeat the probability experiment a lot of times, well, in this case, it may be like 1,000 insurance policies, right? So there is 1,000 women buying these life insurance policies. A lot of them are going to live, right? And every once in a while, one of them will die, right? So the insurance company will collect $530 999 times. And then maybe they will have to do the payout of $249,470 once, right? So overall, for all those 1,000 women on average, right, they're going to make $7.50 on each woman insured. And times that by 1,000, now we're looking at a nice profit, right? Okay, so let's write that out. Okay, so if there are a lot of policies, the insurance company can expect to make $7.50 per client. Okay, so again, the company expects to make $7.50 for each 49-year-old female client it insures, right? So that $7.5 profit of the insurance company is a long-run result. So it does not make, the company does not make $7.50 on each 49-year-old female it insures, but rather the average profit per 49-year-old female insured is $7.5, right? So because it is a long-run result, long-term result, the insurance idea will not work with only a few insured, okay? This is the work of actuaries. Is the one branch that you can go into if you major in statistics, and is to become an actuary, and they set these values for the insurance company, right? And then it helps determine how much the insurance company is going to make. All right, so we've talked about the shape and the mean of a probability distribution. Now, finally, we can talk about the standard deviation of the distribution. Okay, so here is the formula for standard deviation of a probability distribution, sigma of x. Okay, it's the square root, okay, of the sum of x minus mu of x squared times probability of x. Okay, so let's do this one by hand. We're going to be using the same data, which is the Netflix movie data from the previous page. Okay, and we're going to be computing variance and standard deviation. Okay, so let's use this table here to help us determine standard deviation and variance. All right, so I'm going to do the first line with you, and you're going to do the rest on your own, and we'll check the answer, okay? Okay, so first we're going to take the value of x, so I'm going to take 0 here, Okay, and you're gonna subtract mu of x. We found the mean of the distribution table to be 1.49 in the previous page, so that's that. So 0 minus 1.49, which is negative 1.49. Okay, and then you're going to square that value, so negative 1.49 squared. Then you're going to multiply that by the corresponding probability, which is 0.06. So when you do that, you should get 0.133206. Okay, so this is for the first row. Okay, so I want you guys to do the rest. So go ahead and pause the video, finish the rest, and come back when you're done. Okay, magic. All right, go ahead and check your answer here. I mean, these are not really the final answers, but go ahead and check your numbers. Okay, so these are right here, these numbers. So when you add these numbers up, right, you should be able to get 0.890222, right? So that's the variance. So this is the variance. So it's about 0.89, okay. And the standard deviation is the second one. So standard deviation equals the square root of that number, right? So go ahead and use the whole thing right here, this one, and then take the square root of this number, and you should get about 0.93, right? So the units will be 0.93 streamed movies. So this is the standard deviation. All right. Now you can also use the calculator function to get the standard deviation as well. Okay. Basically, you're gonna do the same thing that you did when you found the mean of the probability distribution. So you type x values under L1, probabilities under L2, and then you do 1 bar stats. L1 comma L2, okay, the same way that we found the mean, okay, and then on the resulting screen, you're gonna see 0.93 under sigma, all right? So that's another way to find the standard deviation using your calculator. That's okay too. All right, guys, that's it for this video, and I'll see you in the next video. Bye, guys.